Question 8.
Yes.
The diagram below A decision.
Good. So in this diagram, what they are trying to do is that they are trying to investigate the products formed when hydrated copper 2 sulfate is heated and maybe make observations. So they are asking us that we explain why the boiling tube is put in a slanting position as shown. So the first thing that we have to do is to explain why the boiling tube is put in a slanting position.
Sucking back of the liquid, which would lead to the breakage of the test tube.
Is it sucking back? Do we call it sucking back?
Yes.
Okay, it is the reason why what will happen if it rolls back, it is okay, but it's not called sucking back. Remember, this is hydrated copper 2 sulfate. So when we heat it, it loses the water of crystallization in form of water vapor. So once that water vapor collects, now water, which if it is allowed to roll back, it will break the boiling tube. So in this case, what is the planting position is to prevent water that condenses, or not the water that condenses, it is to prevent the water that is formed on the cooler parts of the boiling tube from rolling back to the hot part of the boiling tube, which will otherwise break the boiling tube. So it prevents the water formed from rolling back to the hot part of the boiling tube, which will otherwise break it. Actually, during any experiment, when you are told to heat a substance in a boiling tube, you are supposed to put it in a slanting position because you are not sure whether this substance you are heating is hydrated or not. So if you happen to be heating a hydrated salt like this one, the water vapor will be lost and it will cool to form liquid water. And if it is not in that slanting position, the liquid water formed will not be moving out, but it will roll back to the hot part of the boiling tube, and therefore it will break the boiling tube. So to prevent this, that is what you have to do. You have to put it in a slanting position. Are we in agreement?
Yes.
So in simple terms, it is just to prevent otherwise break it. Then part B, what is observed in the boiling tube? What observations are we going to make? What observations are we going to make? The boiling tube. Yes?
The blue solid copper 2 sulfate turns to white powder.
Good. So the blue solid changed to, the blue crystals changed to white powder. That is one observation. So the observations here we have mentioned, one, that the blue solid, that the blue crystals turned to white powder. They turned to white powder. That is one. The other one, there is a second observation that is expected there.
Small water droplets are formed on the cooler parts of the boiling tube.
So you don't mention them, you just say colorless liquid. Colorless liquid. Just talk of colorless liquid, don't say water, formed on cooler parts. Formed on cooler parts. On cooler parts of the boiling tube. Of the boiling tube. So there is a colorless liquid being formed on cooler parts of the boiling tube. Then now to explain this, when you heat hydrated copper 2 sulfate, which normally has water of crystallization, it loses this water of crystallization and it forms the anhydrous copper 2 sulfate plus the 5 water molecules, like that. Are we in agreement? So this one here is blue, but this one here is white. So that is why it turns from blue to white, because the hydrated has lost the water of crystallization to form the anhydrous copper 2 sulfate. So that is why it is changing from blue to white. Are we in agreement there?
Yeah.
Yes. So this water formed is in form of steam. So when it cools, that is why it forms the colorless liquid. So that means that we can be able to identify the colorless liquid that is appearing there as liquid G. What is the identity of that liquid G? What is the identity of the colorless liquid G? What will be the identity of G?
Water.
That is
H2O.
water, isn't it? That is water, or somebody saying H2O. Now, somebody can also ask you in an exam that how do you prove that liquid G is water? How do you prove that liquid G is water?
It turns blue cobalt to chloride.
That is anhydrous cobalt 2 chloride. A paper made up of anhydrous cobalt 2 chloride paper, so that now it turns from blue to pink. Or apart from that, you can put it back into the anhydrous copper 2 sulfate. If it turns it from white to blue, then you conclude that that liquid is water, isn't it? Are we together there?
Yes.
Hello?
Yes.
Yes.
Now, somebody else
Yes.
can also ask you that you prove that liquid G is pure water. How do you prove that liquid G is pure water? How do you prove the purity?
Checking its boiling points.
So one thing you can do is that you heat it, and then you, until it boils, determine the boiling point. So pure water boils at 100. At what pressure? So pure water boils at 100. At what pressure?
Atmospheric pressure.
At atmospheric pressure. So you can heat it until it boils. Then you determine the boiling point. Then you say that pure water is supposed to boil at 100 atmospheric pressure. Apart from determining the boiling point, what else can you determine to just ascertain that it is pure water?
Determine its density.
You can determine its density. What is the density of pure water?
Or the
1
density
gram
of pure
per
water.
centimeter cubic.
What is the density of pure water?
1 gram per centimeter cubic.
Good. Pure water has got a density of 1 gram per cubic centimeter. That is correct. Apart from the density, is there any other thing that you can use to prove that that pure water?
Melting point.
Melting point cannot work because it is already in liquid state.
What about the freezing point?
We are talking of a solid, but if it is a liquid, you don't talk of the melting point. What
Then
are you going to talk about?
Freezing point.
Freezing point, maybe if you freeze it, you can talk of the freezing point. That is okay. Where pure water is supposed to freeze at 0 degrees Celsius at atmospheric pressure. Then apart from that, we have the other one, which we call the refractive index. We call it refractive index. We can determine the refractive index. All of you take physics, so by now you should be knowing what we mean by refractive index. What is the refractive index? What do we mean by refractive index? Loci. Loci?
Teacher, I have not yet studied about it.
Yes, yes. What do we mean by refractive index? Any idea?
No idea.
I cannot describe it in physics terms. And what I know is when you have substance a pen, it will bend. And you see that? any pointers we want
Mix and mute.
Yes, you see that?
Really?
So when it bends like that, this angle here is what we are referring to as the refractive index. So each substance has got its own refractive index. So you can try that one even at home. Uchukue maji uweke kwa glass, alafu uingize kalamu. Then you see through the glass. You'll be able to see that when it touches the water, when it changes from one media to the other, there is an angle of deflection. There is an angle where it is index. So every substance has got its own refractive index. I may not be able to explain in physics how we can be able to calculate it, but it has index.
Yes,
Good
yes.
of a substance. Good. First of all, what is happening? If you look at the relationship between temperature and time, between J and R, what is happening? What is happening? What happens to the temperature as time goes?
It increases.
Yes, it increases steadily. So what is happening? Why does it increase steadily? In other words, that is what they are asking. It increases the kinetic energy of the particles or of the molecules in naphthalene. So they move faster. Are we together? They move faster or they vibrate faster because this was a solid. So they vibrate faster. And as they vibrate faster, that one leads to an increase in temperature. So the moment the kinetic energy increases, then the temperature also goes up. So here they are going to vibrate faster and therefore an increase in the temperature. R and L, what is happening to the temperature as time goes?
Temperature remains constant.
Temperature has
Temperature
remained
remains
constant.
constant.
Excellent. So the temperature remains constant. So what do you think is happening to the molecules of naphthalene?
The heat is used to break the forces holding the particles of naphthalene together.
So the heat supplied is being used to break the forces or the bonds that are holding the naphthalene molecules together so that they can change from solid to liquid. So what is the state of matter of naphthalene between R and L?
Liquid.
There is part of it which is liquid, part of it is still in solid form. It only becomes fully liquid after L. Are we together?
Yes.
Yes.
So during melting, part of it is solid, the part of it is liquid. So it's a mixture of a solid and a liquid. So anytime we have change of state of matter, there is a mixture of the two. That one will be maybe if it is changing from solid to liquid, then one will be solid, part of it will be solid and part of it will be liquid. But if it's changing from liquid to gaseous, then we shall be having a gas mixed with a liquid. So it is important to know that when we are having change of state of matter, there is a mixture of the two states of matter, the one that is going into and the one that is changing from. But the temperature has to remain constant until there is full change of state of matter. Like for example, during melting, at R and L, you can see the temperature remains constant because the heat supplied is simply being used to break the bonds that are holding the solid particles together. So this curve, what is the name given to this curve?
Heating curve.
That is called the heating curve. So that curve is known as the heating curve. Are we there?
Yes.
Okay. Good. Can we move to question 7 that is appearing there? And this time round, I will pick on somebody to read for us. There is Jermaine Onyango. Onyango? Onyango, can you read
Both
for us?
diamond and graphite have giant atomic structures. Explain why diamond is hard while graphite is soft.
Good. Why is it that both of them have a giant atomic structure, but diamond is hard while graphite is soft? Now, Arieba, are you there? Is Arieba in the group? Hey, Ariemba. I thought I saw Ariemba. Respond to that.
The graphite has
Yes.
molecules that are held together by weak.
And so that is why graphite is soft. Are you seeing that? So these layers are held to each other by the weak van der Waals forces. So this one here is a here that holds these layers together is what we are calling the van der Waals forces. These are the van der Waals forces. These ones are the ones we are calling is not bonded, is left unbonded, and so it is delocalized within the structure. So graphite has got delocalized electrons. It has delocalized electrons. So that is why it conducts electricity. But when it comes to diamond, all the 4 valence electrons participate in bonding. So this one has no delocalized electrons. No delocalized electrons. So that is why diamond, it is a poor conductor of electricity because it does not have any delocalized electrons. But graphite conducts. Hello?
Yes.
Is that fine?
Yes. Yes.
Now, maybe you can look at the uses of graphite at your own time and look at the uses of diamond. And for each use, you have a reason why it is used that way. Is that okay?
Yes.
You go and look at the uses of diamond and graphite, and for each use, you must explain why it is used that way. Is that fine? Those structures. I'll be calling out what you have drawn. I'll tell you on how you, but I want you to draw the structure A and structure B using dots and crosses. You show the bonding, the bonds that are formed in between sodium and fluorine, and the second one is between carbon and fluorine. Is that okay? So pick a paper and a pen and please draw. Then once you have drawn, allow me to see what you have drawn in your, I'll be able to tell you on how you'll be showing me because you have a camera, you can even just focus on it, then I'll be able to have drawn. I'll select just a few of you to show me what I've drawn, then we agree together on what is supposed to be. So, are we together? Are we together, class?
Yes, yes.
So you have drawn. I hope we are done by now.
Yes.
Okay, good. Now, is this one known as Elijah Mati. Elijah Mati. Elijah. Elijah Aski. Bernard Ngware. Bernard Ngware. That is who?
Otinga.
What you can do, can you put on your video? Alafu uweke hiyo whatever you've drawn on the camera so that I can be able to see. Put on your video, show me what you have drawn in your camera. If you are using a phone, you can just flip the phone kunionyesha what is, you can put it on the desk alafu uonyeshe camera nione what you've drawn. I can see Lokai is trying to show me something, but ionekani. Lokai yako bado hajaonekana. Anybody, if you have done, please, you can show me. So you are able to see the board. So I'm also able to see what you can show me using your camera. I'll be able to see. I can see Elijah Lokai. Lokai, I can see yours. Hiyo ni number 2 ama number 1 Lokai?
Number
Lokai,
2.
Number 2. Yeah, number 2, that is okay. Number 2 is okay. I can see it is correct. Any other person? Huyu ni nani anajiita LG? Yes. Which one are you showing me? Lokai. That is number 1.
1.
Yeah, number 1 is okay. There is this one, Griffin. Ogot, please move it closer. I can't see properly. Yes, that is okay. Ogot, number 1 looks okay. Number 2 is okay. Yeah. Then Daniel Onjari, Daniel, move it closer. Okay, Daniel, I can see number 1 is okay. Number 1 is okay, but I haven't seen number 2. Martin, Karosei. Martin, move it closer, Martin. Yours is a bit far. Okay, that is okay. Number 1 is okay. Felix Karanja, I can only see your face. I'm not seeing what you've drawn. Felix, please show me. Yes.
Madam Kit, you can hear me?
Hello, yeah, I can hear you.
Kindly check on the breakout rooms. There should be something there. Breakout rooms, can you see it? Top right section. Hey, boss. Hey, I'm
Top right.
Sorry, Madam Kit, you can see breakout rooms. Madam Kitty, kindly confirm. Oh, thank you. Yeah, it's worked. The rest of the students who said check on breakout rooms, pick your class, then you can proceed with the rest. You join your class. William, Robert, Justin, and Isaac, do the same.
I can see it.
Robert, you can't see breakout rooms.
Yes.
I think you may need to update your Zoom. Could be an older version. You may need to update it so that next time you don't have to be placed there. You can automatically move in. Just download a fresh copy of Zoom. If you go to Zoom, download client. Next time it will be able to give you that. Which is your class, Robert?
2A.
2A. All right. Any other person having an issue? So Robert, I've already pushed you there. Benjamin, you can see breakout rooms. Yes, Lisa. Hata nimeona uko ndani. That's all. Naweza ndani na class. Naona mko 14 so far, but kuna wengine wanaingia sasa hivi. Nice. So check once you log in, confirm that you can see breakout rooms. Actually, if you can't see breakout rooms, it means you have an older version of Zoom installed. You can download something from zoom.us, a fresh client. Then you'll be able to see that. But if you can't see it also for now, you can let me know. I can push it to your class. Mwalimu is already in class. She's already teaching. Breakout rooms, then you pick your class. Hello, good morning. How are you? Nyinyi sijaona mkifunza classes online. Kwa nini? Sijaona mkifunza online classes. Which class? Which class? 2R. Let me check. Did you register? Did you register?